Okay, so now what we need to talk about is the sampling distribution of a proportion. At the last little discussion I had, we talked about the sampling distribution of the mean, a sampling distribution of the proportion is very similar. So I will not go through the full theorem proving by example. I will just kind of get to the gist of it. So if we have a what we call the point estimate of a population proportion is called p hat. And so as an example, if we have a sample of 200 semiconductor controllers, and 4 are defective, then, and the problem asks you to find the point estimate for the number, or for the proportion of defective semiconductors. It would be as simple as saying p hat is the point estimate, and it is 4 out of 200. Likewise, if we wanted the complement to that proportion, right, the complement to that proportion would be the non-defective controllers or semiconductors, and the complement is denoted by 1 minus p hat, which sometimes we call q hat, and that would be 196 out of 200. So that would be the point estimate of a population proportion and its complement q hat. If we wanted to talk about the distribution of p hat, the sampling distribution of p hat is the same as the proportion, which is all coming from the binomial distribution, where you have one of two outcomes and you do it a whole bunch of times, like flipping the coin or looking for defective or non-defective controllers in a manufacturing process. That sampling distribution, the mean of p hat is just equal to p, or the overall population proportion, and the standard deviation of p hat is equal to the square root of p hat times 1 minus p hat over n, or the square root of p hat q hat over n. And again, this is the same really standard deviation of the mean of the population proportion. And what we need to do this for is we really need to start building confidence intervals around that. So I'm going to stop this lecture and start a new one that has a lot more detail about the inferencing of these two ideas.